Hey, it's Jim, and this is FRM Part 2, the topic on market risk measurement and management, and the chapter on beyond exceedance-based backtesting of value-at-risk models. I'm going to go ahead and editorialize right away. Exceedance, I'm not sure that's even a word. In fact, in the first couple of pages of this chapter, the authors say, you know what, you can use the word exceptions or breaches, but we'll go ahead and stick with exceedance. You guys know I like to remind you where we are in our life with each one of these chapters. So let me just remind you that the very beginning of this topic, we had great conversations on both value at risk and expected shortfall. Then we went through some measures of how to estimate those two metrics. And then we did some back testing in one of those early chapters. And remember, we did things like historical simulation and Monte Carlo and failure rates. Well, now what we're going to do is we're going to go ahead and jump into some pretty substantial and complex statistical models to perform even more accurate and better measures of how well the value at risk models have performed. So let me just remind you, all we're doing is saying something like this. Hey, the model says that we can expect, let's just say over the next week, we can expect 10 in value at risk. And what we do over the next 10 days, we observe what happens. If we only have 6, well, that's no good. If we have 16, well, that's no good, right? What we're trying to do here is we're trying to compare the difference between what we expect to happen and what actually happens. And those things should probably link. Now, of course, we'd much rather have, even if we expect 10, we'd much rather get 6. But what we're trying to determine here is the accuracy of our model in its ability to forecast. All right, just for learning objectives, we're going to talk about properties. We're going to talk about this PIT. This is really a cool thing. We're going to look at some graphs, and I'll explain a couple of things that go on inside of this chapter. We'll need to know the shape of the distribution, and then we'll end with a couple of tests, 3 of them to be exact. That Kolmogorov-Smirnov test is more emphasized inside of this chapter than the other 2, even though the other 2 they cover for one of the big weaknesses in that KS test. I wonder if you're like me. Before I have been going through this FRM program, I never heard of these tests, never heard of these dudes. Maybe you guys have better than I have. One thing I've learned is that there are a million econometrics tests out there that I never heard of. So I did a little bit of research, and I'll just tell you something very sad. This Kolmogorov dude, his mother died during childbirth, so he went through life without a mother. But by the time he was 5, he was able to do all sorts of crazy math stuff. So, all right, you ready? Let's go to this exceedance-based. How about if we call it a breached-based back test, a BBB? That's what I would probably have called it if I were in charge. So all we're doing is validating. That's important. So I said this earlier, right? Comparing realized outcomes against those forecasted values. Now, one of the things that impresses me about GARP is the simple fact that they are keenly aware that there are lots and lots of really smart men and women who work inside of these banks, but there are also lots and lots of really smart men and women who work for regulatory agencies or government agencies or the SEC, whoever it is out there. And so these two groups of people have to come together and come up with some reasonable model. And so I'm guessing you've noticed this, especially back in part 1, that GARP is very aware that those internal models have to be super accurate, but they have to satisfy the regulatory constraints that are out there. So these two groups of people who sometimes have competing goals have to figure that out. I'm not sure if that's a really good exam question or not, but I would just be aware of the simple fact that we've got the internal models, we have the regulatory models, and those two things should complement each other and give us a better sense of the total risk that's out there. 2 primary properties for these value at risk models. To be accurate, they must have unconditional coverage. which simply means that the actual breaches matches the expected breaches at some predefined level. And there we go, 99%. And so the chapter uses 99% because that's what the Basel people tell us should be. But I want to give you just kind of another example. You guys know I love sports. And so remember back in the old days when Tiger Woods was really good, and maybe he'll return to that after he recovers from all of his health issues. I want you to think about a model that predicts his performance during the course of a golf tournament. Now, those of you who are golfers know that they play 4 rounds, that's 72 holes, but let's just suppose they play 100 holes. So there's our data set. And so what we could say is that our model predicts that of those 100 holes in this tournament, Tiger's going to have 1 double bogey. Remember, value at risk is that left-hand tail. So for Tiger Woods and these golfers, double bogeys and triple bogeys, and even bogeys, they're not good outcomes. So our model predicts that, let's say that Tiger's going to have 1 double bogey during the course of a golf tournament. Well, if he has 7, then we're no good. If he has 0, then we're no good. Now, that's not going to be, kind of a normal distribution or any kind of a regular distribution. But you get the sense that what we're trying to do is we're trying to accurately predict how many double bogeys Tiger is going to have. Here, we're trying to accurately predict, are we going to have losses that exceed some reasonably expected kind of a loss. And of course, we don't want to have any of these losses, but we know there are things like, macroeconomic conditions, industry conditions, bank-specific conditions that are going to contribute to those left-hand tail losses. So unconditional coverage is one, and then independence is another. That simply means that if we have a breach yesterday that we shouldn't have one today, or the probability of us having that one today is back to whatever that 99% confidence level is. So unconditional coverage and independence. This is probably a good exam question in which GARP says, hey, here's some characteristics. Which one of these is appropriate? Now remember that several chapters ago we talked about some kind of traditional ways of back testing, and that's exactly what we're doing now. Compared to what we did before. Remember there was a chapter in there where we looked at things like failure rates, which just meant that was a first initial term for breaches. But now what we're going to do is we're going to look at an entire probability of these things, and this is called a probability integral transform. So notice what the bolded thing tells us there. It's an alternative perspective to what we did multiple chapters ago. Instead of looking at just the failure rate, we're looking at the distribution so that what we can do is reach in and extract out a probability of observing a loss that is greater than whatever that realized P&L was. And that's based on the previous days or the previous week value at risk model forecast. So think about the difference between those traditional models and what we're doing now. In the old days, we would just say, all right, let's just wait and see what happens. We thought it was going to be, what did I say with Tiger? We thought it was going to be 1 and it's 2. We just wait. But now before Tiger goes through the tournament, we're going to say, hey, you know what? His probability of observing a loss is 1% or 5% or whatever that is. So here are the properties once again. So we need to have a uniform distribution. Remember, that's the interval of 0 to 1. That just simply means that every possible outcome has the same probability. I always like to use the flipping of the coin or the rolling of the dice. And when we do the rolling of the dice, I can't help but remind myself of that awesome 1971 James Bond movie, Diamonds Are Forever, when Sean Connery goes to the craps table and he bets all this money. He wins $50,000. I'm pretty sure that the roll of those dice during that craps game, and by the way, he has a helper there, for those of you who don't know that. And he wins $50,000. I have no idea if the probability integral transform model would have predicted that James could have won $50,000. Probably not. But we know that the roll of a dice is going to be uniformly distribution. Remember, think of it this way, and I hope I'm not offending you and reminding you this. Remember, they call it the rectangle distribution because if you draw a picture of it, it looks like a rectangle. Independence, the series should be independently and identically distributed. Let me just quickly remind you, that means that the terms of the sequence are mutually independent, and then those terms all come from the same probability distribution. What does that mean? That just means that each data point in that sequence is unrelated to other data points, and they all come from the same underlying distribution. Now, if in fact we go ahead and observe this distribution and it doesn't look like a rectangle, maybe it has something above, or maybe it has something below, maybe it has a high middle, maybe it has a low middle. Well, what that means is that the model is not perfect in its explanation. But what's really cool about these tests that we're going to talk about in a little bit is that even if we get a non-uniform PIT distribution, what we can do is we can learn from our mistakes. It clearly tells us that something's wrong in the middle, or something's wrong at the left tail, or something's wrong at the right tail. So notice that second diamond point. If we have a non-uniform distribution, it could mean that we have conservative risk estimates or aggressive risk estimates that come from that value at risk model. Here's a couple of steps to derive the PIT. I would go ahead and just memorize these. However, just remember what I said in the introduction. What we're going to do is we're going to establish that predictive distribution. Whatever that distribution is going to look like, maybe it's going to look like a perfect rectangle, but maybe it'll look like something else. And then we're going to observe the profit and loss outcomes, right? We can do that. And then we're going to compute those CDFs. And from the CDF, we can obtain the probability integral transform value, and then we're going to assess the uniform distribution. We're going to compare, and we'll see this in a graph here in a little bit. We're going to compare that empirical distribution to the uniform distribution, and if it looks like a perfect rectangle, we're going to say we have a perfect model. But you guys know probably better than I do that we're not very likely to come up with a perfect model. But the cool thing, and I'm repeating myself again, is that whatever kind of mistakes that the model makes, we can go back and adjust the model to cover for those mistakes in future forecasts. Remember, we like to be perfectly forecasting today and tomorrow and next week, but that's just not going to be possible. All right, how about the shape of the distribution? How that can be used as an indicator of the quality. This is just what I was talking about here in a second. And here, let me go ahead and show you this. Not these, but these things down here, I'm going to show you when we look at that KS test here in just a second. So just bear with me for just a second. So by plotting these, a well-calibrated model should exhibit the rectangle, right? And that should make perfect sense. But notice that second diamond point. I think this is probably a really good exam question. What if GARP says, all right, here's a perfect rectangle today, but we don't have a perfect rectangle tomorrow? What's the problem with that? And you could say, well, there's a lack of consistency. Remember, throughout part 1 and part 2, I try to use the word sustainability and consistency. Here, this consistency is going to describe the well-calibration of the model. All right, so what are some problems here? So go down to the bottom left. No problem if we have a uniform distribution, because then it captures that entire distribution, that entire scenario of risk outcomes. But what if we have clustering? What if there's clustering in the middle? What if there's clustering on the outskirts, in the tails? So look at that middle second bullet point. This is a great exam question here. Clustering in the middle, too conservative. Clustering in the tails doesn't fully capture tail risk, so maybe that's aggressive. But then skip over to the far right column in orange. What if we have some kind of skewness that shows up? Or what if we have kurtosis that shows up? Notice this indicates a need for adjustments. So this is what I was telling you about. We're reaching in and extracting information from the model to help us improve. Now what we can do is we can use histograms or the double Q plots. In a second here, we're going to look at these three tests, but based on what we said in that previous slide, notice if there are masses in tails or if there are masses in the middle. Maybe I can call that middle concentration. So there's aggressive versus conservative. I wouldn't be surprised if on the exam you saw some of these distributions and you could clearly say, hey, something's going on in the left tail, something's going on in the right tail, something's going off in the middle. Look at that normal distribution there in the two in the middle. You have a little bit more there over in the positive end. On the bottom one, you have a little bit more over there on the negative end, which indicates some aggressiveness or conservativeness inside of that model at different points. And so what you can see is where along that distribution is the model failing. So once again, you get to see and you get to improve. Goes back to that great comedy, that great comedian, Mitch Hedberg. You guys know who Mitch Hedberg is? Sadly, he lost his life years and years ago. But he said he did a set at the Improv the other night, and it didn't go very well. So when he came back the next night, they added an E to the sign, and that's what we're doing. Mitch Hedberg wanted to improve. That's really clever, by the way. I'm hoping you guys laughed a little bit. Anyway, this is what we're trying to do. We're trying to improve, and so you compare these distributions. All right, what do we know about all these dudes here who came up with these tests? So comprehensive method, robustness, predictive distribution, all right, model accuracy. So that makes perfect sense. And you know what? You could apply those back to that earlier chapter, although you probably would have to take out the word comprehensive because these are way more comprehensive than what we did before. All right, so let's do this KS test. Let's go ahead and spend some time trying to determine why GARP and the authors used these tests, which are way more comprehensive. So here's this KS test. What it's going to do is it's going to compare that empirical distribution, which we can observe, with the reference uniform distribution. Now, the authors in this chapter, they use the term reference distribution multiple times. And so I don't want you to get confused. The reference distribution is going to be the uniform distribution in this value at risk back testing. I'm guessing that KS, when they put this test together, that it could be used for lots and lots of different types of distributions, but in this case, it's just the reference distribution. So what we're doing is we're measuring the maximum distance between those two functions. If you take a look at the chapter, boy, there's lots and lots of stuff in there that is confusing if you don't have lots of calculus in your background. So what I want to do is simplify it for you. All we're really doing is taking a ruler. The ruler is not the tool, but we're taking a ruler and measuring the distance between 2 points. And it's taking the maximum distance. So make sure you remember maximum distance for potential exam questions. So let's go ahead and look at what's happening at the bottom. Look on the bottom right there, this PIT distribution. Notice that says all sub-portfolios. So let me just remind you of what the chapter tells us. They have about 700 or so portfolios from about, I think it's 20 different commercial banks or investment banks. And they rank these portfolios. So there's a total of 700 in them. And what they do is they lump them all together so that all those sub-portfolios are combined. That's what that is down the bottom right. On the bottom left, these are top of the house distributions. So these are within each firm. What did I say? I think there are 20 different firms in there. So what we're doing is we have two different graphs for each top of the house and the PID sub-portfolio distributions. So notice the first one on the horizontal axis goes from 0 to 1. So there's the entire there's the entire distribution. So if it were perfect, notice there's that line, what is that, around 5. So if this were perfect, that would be the perfect rectangle. Skip over to the sub-portfolios, that would be the perfect rectangle. So clearly you can see that the sub-portfolios have lots and lots of stuff in the middle, and the tails dip even further. So for the in-house or inside of each of these 20 firms, the KS test looks okay. I mean, it's not perfect. It's not a perfect rectangle, but you can see that there's a problem in the tails. All right. And then notice that the next two graphs, these go from 0 to 0.05, 0 to 0.05, but we're adhering to the Basel rules. So there's a 0.01 in there. So that's okay. But look at down in the sub portfolios. There's that one spike over in the left tail. Now, the problem with the KS test is that look at that last bullet point. It may miss specific tail specification. So we call that misspecification down there. So that's probably another good exam question. The KS test, it's a good one to start, but it somehow doesn't always capture that tail risk, which brings in this next test, the Anderson-Darling test. I have no information on these two people here. So it's a modification. It assesses uniform calibration, but notice that, what is that, about the 5th bullet point down there? It's useful in detecting biases. It's way more computationally intensive, and it's sensitive to small sample sizes. So make sure you know those last 3 bullet points. Now let me go ahead and just skip over to the Cramér-von Mises test. What this one does, remember back here, both of these tests, maximum distance, okay? This test here uses the mean squared deviations, so it's a different kind of a ruler. What this does then is that it detects deviations in both the middle and in the tail. So this is what we're doing here. So we like the KS test, but it has a problem with tails. We like the AD because it contributes to our understanding of the tail, but it has a couple of drawbacks. The CVM test then adds the middle point, so it provides balanced sensitivity. Now, let me go ahead and tell you, you should be saying to yourself, okay, Jim, well, go ahead and draw some of these graphs here. Well, what the chapter does is it doesn't draw graphs, but what it does is gives us a bunch of tables in which we're identifying how many of those in-house and sub-portfolios, how much of those passed the test with this CVM test compared to the others. So I'm not sure that those results are too terribly interesting from a test perspective, but make sure that you know things that are on that, all the items that are on that slide. So that was a relatively short slide deck and recording for, a chapter that is fairly comprehensive. So notice that the learning objectives just tell us to describe and describe. So all of the math stuff in there, you're not going to have to do any calculations, but you might have to interpret some of these results. Once again, look for that rectangular distribution. All right, hey, thanks for watching. I know you're busy and you got lots of other things to do. I appreciate your time invested in what we're doing for you guys. I hope it's worth it. So thanks for watching. Have a great day and good luck studying.